So, so today we'll start something new that is called okay. So today we'll start the closure, of a set. What is closure of a set? Let A be a let X here. Yes. Right. So let X comma D be a metric space. And a subset of X, then the closure in the closure of A, which is denoted by A bar is equal to intersection of all closed set which contains okay. So closure of A is nothing but intersection of all closed set contains A, since arbitrary union union means intersection arbitrary intersection of closed set is also closed. We can say that A bar is nothing but smallest closed set containing Now we are moving on to some, again, very important result. What should be the result? Some very, very important theorem. Let E be a, yeah, pardon. Let A be a subset of X comma D. Then we can say closure of A is nothing but A union derived set of A. And prove this. So on the last two classes, so we learned how to find derived set of different kind of sets. And yeah, and now if we prove this result, we will be also able to find closure of any set. So proof. Proof is like that. Our first goal is to show that so our first goal is to show that A union DA, it is closed, i.e. A union DA complement is open. A complement intersection DA. Okay, complement is open. So we'll start with like that. Let X belong to A complement intersection DA complement. Then what we can achieve? X does not belong to A and X does not belong to D, right? So basically, there exist R greater than 0. There exists R greater than 0 such that B of x comma r intersection E is okay. B of x comma r belong to A. Okay, and so basically we get B of x comma r belong to sorry, not belong to B of x comma r, that is B of x comma r, that is subset of A complement. And suppose B of okay. And suppose B of x comma r intersection of derived set of A is non-empty. Let y belong to B of x comma r intersection D. Okay, and y belong to B of x comma r intersection D. Then for any epsilon greater than 0, B of y comma epsilon intersection B of y epsilon intersection B, that is equal to non-empty. But B of, so basically we are trying to do like that. So suppose you have a ball and this is x and this is r, and since it's an open set you will get again so it's inside y. So if y inside it, actually you can get again an epsilon actually, but B of x comma r is open, right? Then we should have B of, we should have delta greater than 0 such that B of y comma delta inside B of x comma r. Yeah, that's possible. And B of y comma delta intersection E is obviously equal to empty, as B of x comma r intersection which is empty. So it's a contradiction, right? It's a contradiction. So this one, if we take it as 1, so 1 is a contradiction. So 1 is a contradiction. Yes. Then B of x comma r also belong to D a complement. D a complement. So if we combine these two cases, we are getting that B of x comma r lies inside a complement intersection D a complement. So a complement intersection D a complement. This is actually open. Hence, A union D. This is actually closed. Now, what we learned in the definition of closure, a union. It is like it is like inside all the closed set containing A. Now, A bar should be is equal to what? Inside A union D, right? Now, what we have learned in the previous day. Now A bar is closed. So it contains all the limit points of A bar, i.e. all the link points of all the limit points of A. Hence, A sits inside A closure, obviously, and DA, that is also sits inside A bar. Then we can combinedly write it as A union DA is clearly subset of this closure. Combining 2 and 3, we get A union DA that is equal to A closure. That's our goal. Is the proof clear to everyone? It was a bit long proof. Hope if you guys have any doubt, you guys can say. It was a bit long proof. So first we prove that this is a we have to prove that this is a closed set, and for using its complement is open. Then we take arbitrary point inside it, and then we show that there exists an r greater than 0, which should be inside actually the intersection. First we showed that it is intersection A complement, and then we showed it's inside the complement of the derived set by using contradiction. We use lot epsilon delta here, and B of x comma r is nothing but subset of A complement intersection D A complement. So A complement intersection D A complement is open and A union D is closed. And the rest of the work is trivial. We are using the previous day result, and now we are done. Now we are defining interior of a set. Let again is a subset. Yes, subset of x comma d. Then interior of A is denoted as this type of thing, or sometimes or sometimes A union, or sometimes interior, or sometimes interior of A. Yes. Or sometimes interior of A, as it is defined as. It is defined as interior of A. Sometimes this as union of all open set contained inside A. Since arbitrary union of open sets is open, then we have interior of A is largest open set contained inside A actually. Okay, so for example, so what if we take any finite set Xn interior? So in usual metric, in discrete metric, can anyone please answer this one? What is the interior of a finite set? X1, X2, dot, 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 Xn in usual metric and in discrete metric. Can anyone please answer?
ইউজুয়াল মেট্রিকে ফাই হবে আর
Hmm.
ডিসক্রিট মেট্রিকে সেটটাই হবে।
একদম. So as Anit is speaking that in usual metric, it should be phi. And in discrete metric, that should be simply the same set. Why it is? Because you can take the minimum of the distance between xi and xj, and you can construct a ball. So whenever you so whenever there is an open set inside it actually, so you can construct a open ball inside that point, and with the radius of minimum of the distance between d of dxi dxj, then you will get its phi. And in discrete metric, every singleton is an open set. So every singleton is an open set, so their union should be open set. So it's automatically an open set. So interior of this set is also open set. Good. So we'll get into some small results. Some results. Some of them are trivial and some of them we need to prove. So first of all, we are defining interior of A is nothing but sitting inside A. And it is also sitting inside A closure, which is trivial. Number two is A is open if is equal to A. A is closed if and only if A closure is equal to A. Number 4 is if A subset of B, then A subset of B implies subset of B. And 0.5 is then 0.5 is A A is inside B, then closure union closure. Number 6 is A intersection B. Its interior is nothing but is equal to interior of A intersection interior of B, and A union of B interior is nothing but subset of A union B. So probably I mistakenly wrote it in the wrong direction. Yeah. Okay. What should we write? 7. Yeah. Is here right now. Yes, so it will be like A intersection B. If you take the part, you will get subset of A intersection B bar closure, and if you take union, we'll get and often at the right point we are getting A closures A interiors interior is nothing but is equal to A interior A closures closure, that is nothing but A closure. So we can prove them one by one. So first few results are very trivial. First of all, obviously A interior is inside A because A interior is nothing but the largest open set inside A, and A obviously should be a subset of A closure because A closure is the smallest closed subset of X comma D which contains A. This is done. And A is open. A is open means A is the largest open set containing A. That's why A interior is equal to A. And A interior equal to A, that means actually largest open set containing A, that is equal to A. That means A is open. Similarly, you can say that A is closed. Implies this one A closure is equal to A. And if A subset of B, that implies A interior is equal to B interior. We can start from here. Let's go. Groups. So 1, 2, 3. Trivial. You guys can check. And what about 4? Just a minute, guys. Okay, so 1, 2, 3 are like trivial. You can check. And what about 4? So A subset of B implies interior of A is inside interior of B. So what is B interior? So B union is union of all open subsets. All open subsets. All open set containing B. Which clearly contains all open subsets. Because which the open sets which contains B, obviously it will contain A, na? So it is equal to that's proved. So 5 is similar to 4. You can just use here we use the union, you guys can use intersection there. It's like basic. So what we are left to check? So what we are basically left to check? We are left to check this one. And A union, A intersection B. Interior. That is nothing but is equal to A interior intersection 2. Yeah. Intersection B, intersection B interior. Okay, fine. That is. So suppose we are taking X belong to A union B interior. So A intersection B interior is the largest open set inside A intersection B. Mhm. Mm, largest open set in largest open set inside A intersection. That is equal to union of all open set inside A intersection B. So you can write it as it is intersection of all open set inside E and intersection all open, sorry, it should be union all open set inside B. We are using basically the set theory property, that is nothing but A union. Oh, yeah. Oh, sorry, sheet. It should be union, and this should be again union. This should be again intersection. That should be again. Now, what we are left to prove? I left to prove that A union B union, that is inside A union. That is from the previous result. So A union, that is intersection, that one, and B union, that is inside A union. That's why A that is equal to A union. Proved. Okay, so now we are moving on to this result.
Sir,
Yes.
so can you give any counter example for the equality condition?
So you are wanting some counter example for the equality condition, right?
Yes.
Okay, fine. Uh, okay, let me just find it out. Okay, so you can take Q and Q complement. What is interior of Q and what is interior of Q complement? Both should be phi, right?
Fine.
Isn't
Yes.
it?
Yes.
And what is Q union Q complement? That should be R, right?
Yes.
And what is a interior of R? That's complete R, right?
Yes.
So you're done, right? So as he said, for the equality condition, so take A is equal to Q and Q complement the set of irrational. So both A interior and B interior, that is equal to phi, and A union B, that is equal to R, and A interior union, B interior, that is equal to phi, is subset of R, that is equal to A union. Now you can just check A intersection B closure, that is subset of A intersection B closure. Okay. So as you know, so that is obviously inside A intersection B, that is obviously inside B. So if we adjust them, we can write, combine them, we can just write, that is, B closure means, that should be inside A. Hope it's clear. And for the rest of the project, and A union B. What is this? This is actually A union B, union derived set of A union B, right? And what is this? On the previous class, we have studied that derived set of A union B is nothing but derived set of A union derived set of B. So we can write it as A union DA union B union DB. That is simply is equal to A closure union B closure. And for if you again want to conclude the equality case, you can just take A is equal to Q and B is equal to Q complement. Their intersection is phi, so their closure is phi. And if you take both of their closure, that should be equal to R. And intersection of their closure is equal to R. Then you are done. Now we are going on to the last boundary. Boundary of a set. Let A be a subset of X, D, then boundary of A is denoted as, let's write it as boundary of A. Sorry for the not responding. Boundary of A. And it is defined as boundary of A is equal to the points which are in the closure but not in the interior. That is the definition of the. So as you take any open circle, so what will be the boundary? It is its original boundary. The open the interior is the open part inside the circle, and the closure is the actually closed unit ball. Actually, if you just minus them, you will get the usual boundary. So this is the boundary. That's why the boundary cannot. So in today's class, we have probably actually defined interior closure and the interior closure boundary, and there are some specific properties. And in the next class, we are going to just let a minute. Okay, and in the next class, we are going to discuss some dense set, nowhere dense set, and we are going to solve some problem. Okay. So thank you, everyone. Good night. You guys can leave. Class was good. People use a lot of computer a lot. Use the good. Guys, I'm on a computer for rupees 1.4. अच्छा चेस पे हाँ यूज करते हैं सुपर कंप्यूटर